Hi there. Well, tonight I'm going to show you a project I've been working on for the last 3 or 4 months, and it's this linear amplifier. And it's taken me a bit of time, but so I think it's been all worth it. It seems to work pretty well. And what we'll do is have a look inside it, show you how it all works. It's been a bit of a labour of love, but I think that it should be quite interesting for those who want to build a high power linear amplifier. And we'll have a look inside it, have a look at the top and the bottom, which has got the big power supply, the high voltage power supply, and show you what's what. Right, I've pulled the amplifier out of its little corner, and there it is. As you can see, it consists of 2 parts. The linear amplifier is on top, and we've got the power supply at the bottom. So this amplifier is actually based on the 2 Russian pentodes, the GU81M, and the valves are located here at the back. There's 2 of them there, and I'll just pull this one out. So as you can see, these are really quite enormous valves, used by the Soviet Red Army, probably for radio transmitting equipment, probably VHF, UHF, and they really are quite chunky. Specs of these valves can take up to about 3.5 kV on the anode, and the heater voltage is about 12 at 10 amps. 12 volts at 10 amps, and they also have a screen grid as well, being a pentode, which takes about 800 to 900 volts with that sort of anode voltage, and quite nice actually. Quite I rebuilt this valve for the this amplifier, not so much for the performance. I'm sure there are actually better ceramic tubes out there, but I quite like the aesthetic appeal of these glass pentodes, these big power tubes, and I thought it'd be nice to build up an amplifier. So just put that down to the side for a minute. So that's the rear of the amplifier, and that's the RF connector, the output connector. The other valve, you've got the anode top caps there with anti-parasitic chokes. And moving round, we'll take the lid off in a minute. It's all handmade. All the metal work's been done by myself. There's a lot of metal bashing involved to get this amplifier in order. The main controls at the front. We have standard monitoring, plate voltage, plate current and anode current, and then on the we have an inductor for tuning, plate capacitor, the load capacitor, and the band switch is down here. And all the band switching is done by relays inside, which I'll show in a minute, and some essential warning lights, the HT, there's a fault warning light, and also transmitting switch. On the bottom part of the amplifier we've got the power supply, and again the high voltage power supply, standard metering indicating the HT volts. And below we have a number of indicators for the HT, the screen voltage, and what I've done here as well, which again I'll show in a minute, the rectifier is a standard semiconductor bridge rectifier for the HT, but for the screen volts I've got a hybrid bridge rectifier. One half is semiconductors, the other half are those 2 866 Mercury Arc Rectifying valves. Again, not essential, just aesthetics, and it looks quite nice when they're glowing. Right, okay, so I've taken the side panels off the power supply, and we'll go through all the various components. Essentially, we've got, if we look at the under compartment first, there's actually about five. Let's have a look. 1, 2, 3, 4, 5, 6 transformers in here, and each one does different functions. So at the back there, this is a 10 amp variac, which controls the voltage input into the main HT transformer. This transformer here is a 2.8 kV transformer, HT transformer, and provides a 2.8 times 2 kV at about half an amp. Now this is an XMOD transformer, and the ratings on these are usually for sort of continuous use. So for amateur and everything, it's probably you can probably get a lot more amperage out of it. This funny shaped transformer here is it's a filament transformer for the 866 Mercury Arc Rectifiers, and I got this one off eBay, and I think it was originally designed for some sort of equipment where the original rectifier would sit on the top there, and the output voltage is I'm actually using it on 5 volts, 2.5 the center tap, and that's quite standard for these sort of rectifying tubes. This one here is a filament transformer, which is actually wired back to front. So I'm taking a 10 volt winding from the transformer at the back there, which is the screen supply, and it goes into a 6.4 secondary winding here. When this supplies my negative bias, which gives me about offload about 400 volts once it's rectified and filtered. At the back, that small transformer here, right at the back, is I can probably zoom in a little bit. That's just a normal 12 volt, well 12 0 12 transformer supplying relays and the other electronics. So that's more or less what we've got on the lower rack with all the various transformers. The main problem that we have with so many of the transformers is that you do get a bit of noise. We get an bit of AC hum, particularly on load, and that seems to come mainly from the variac. I have tried to wire out the variac, but unfortunately the problem is the offload voltage on the HT transformer is very high. It goes up to about 420, 4.2 kV, 4,200 volts, which is a bit too much really. So hence the reason for the variac. Okay, moving up onto the next deck. This is where most of the electronics are situated. So right at the very back here, we've got about 4 big, large 100-watt resistors, and that's the bleeder array for the HT. We've got about 10 450 microfarad capacitors wired in series, and this is gives us our high voltage smoothing. And you can see that there's individual 470k resistors across each of these capacitors. Now originally that was the original bleeder arrangement, but I found that the bleed rate was too slow, so I decided to go for these slightly bigger and slightly smaller value resistors. So the total on there is about 100. I think it's about 100k or 120k. So the bleed rate is much faster, but obviously they draw a lot more current, and they do get quite warm. Moving down to this board here, we have on this side all our diodes. These are just standard 1N2 5408s. I've got about 5 or 6 in each leg, and these are arranged in full wave rectification. So each winding, each half of the winding of the HT transformer. So you've got 2.8, 0, which goes to ground. That's the center tap, and the other input goes on the other side, the other leg of this string of diodes. And you can see each diode's got snubbing resistors and capacitors across each one, which is usually recommended for high voltage stuff, so it cuts out the interference from the switching. Along here we've got, this is our basically the bleeder voltage multiplier for the metering. So there's about 10 or so 1 mega ohm resistors in series, which will then reduce the voltage down so that you can read it on the standard milliamp meter. I'll give you a voltage, output voltage. So at the back, at the very back there, over here we've got some boards for rectification, smoothing capacitors for the screen. There's a number of relays here, which are part of the soft start system for the HT. Obviously, when we're running this type of voltage, when you switch on, you get a massive inrush current, so you need to have some sort of soft start mechanism, which is often required for high voltage power supplies. In the foreground here, these are our two 866s, Mercury Arc Rectifiers, and these actually are in the screen supply, and they basically form half of a hybrid bridge rectifier. So the other half of the bridge rectifier which is situated over here, is just standard silicon diodes, 1N5408s wide in series, a couple of them. You don't need to have too many because obviously the voltage is much smaller compared to the HT. And then the other half of the bridge rectifier are these two 866s. I mean, these aren't strictly necessary. I mean, most people would probably go for standard, silicon rectifiers. But these are really just for a bit of fun, really, if anything. They look good, especially when they pass a bit of current. They glow a lovely blue colour, and if you've got the transformer and the transformers available, they do make the power supply just a little bit more interesting, because otherwise it's just a huge lump with just transformers in it, and it's not really that much fun to look at. But those had an interesting touch. What else can I show you? Well, here, this is the high voltage relay, the cutout relay, and we've got some interesting electronics over here, which is really just a trip circuit. And you'll notice there's a few resistors here in series. So this is on the negative leg of the HT, and this board, we've got an op amp, and it's basically detecting the voltage across those resistors, and if there's excessive current draw, the negative volts appear across those resistors, and then are fed into this op amp. It's a dual op amp, LM3485 as far as I can remember, and that inverts the voltage into a positive voltage, which is then fed to the other side of the op amp, which is a dual op amp, which acts as a voltage comparator with a reference voltage. So we've got a reference voltage here, which is adjusted by this trim pot here, and that triggers a MOSFET, the gate of a BS170 MOSFET, which will then operate the relay. So if the current draw is too excessive, you get a excessive voltage, a negative voltage, which is then converted by the electronics to trip the main relay. That's the secondary relay, which operates this big high voltage relay here. This is a proper high voltage relay, which you can see on insulating, porcelain insulating or ceramic stands, which could then trip the HT. If you're building these sort of high voltage supplies, you've got to have a number of safety features in there. It's usually good practice. That here is a 10 ohm wire wound resistor, which we call the glitch resistor, and that's again in series with the HT. So if there's a sudden current surge, that will also blow if for instance this doesn't. So it's all a number of safety factors that you have to take into consideration when you're dealing with such high voltages. It's really designed to be quite an industrial power supply, and you know, if you pay attention to these details, and you make it relatively safe, and it should provide, you know, good years of service. Most of these parts, incidentally, that I've collected for this supply, most of them are all second hand. A lot of them came from eBay. There are one or two new components, but you know, you can source the components fairly easily. It's quite easy to find. So I think that's more or less the power supply in reasonable detail. What we'll do next is we'll go and have a look at the linear itself and take you through that. Right, coming to the main amplifier itself, I'm going to show you first the RF deck, and this is actually fairly standard with one or two exceptions. So I'll start at the back. So the two valves, as I mentioned, are at the back here, and there's a protective stainless steel grille because of the HT, because we've got potentially over 3 kV on the anodes of these valves. So we've got basically a nylon insulator here, and that is our copper support really for the two anode top caps with the antiparasitic chokes on that side. Pretty standard really. We've got the DC blocking capacitor here. It's a ceramic doorknob capacitor rated at 12 kV, and I'll talk about this in a minute, this and that, which is actually part of the plate choke. So the RF output is there, standard piece of RG213 without the coax on, and this is our safety RF choke here. If the doorknob capacitor fails, the DC blocking capacitor fails, then the whole idea of this is that it shorts the HT to earth, and therefore blowing the fuse in the power supply, because what you don't want is DC on the antenna. So the actual tank circuits and the configuration of the C1, C2 is pretty standard. It's a standard pi network, and we can see here the tank coil. Starting with the tank coil, we've got a variable inductor here, which really acts as a trimming capacitor and accommodates the higher frequencies, which you can vary and get the exact inductance. Here we have the main part of the tank coil, which essentially does 7 and 10 megs, and then a small add-on coil there for 3.5, because the actual amplifier covers from 3.5 to 10 meters. I didn't include 160 because I don't really use it that much on 160, and I've got other amplifiers which will cover that frequency. So the variable inductor is quite interesting. On the higher frequencies, because of the high internal capacitance of the valves, you have to use we don't use the plate capacitor on really from about 14 megs and up really. This is actually switched out by a high voltage relay. So all we're relying on is varying the inductance and the load capacitor down here to tune up on the higher frequencies. All the other tappings on the tank coil are varied by vacuum relays here, rather than having an RF switch. Plate capacitor here is standard vacuum capacitor. Actually, this is again from sourced from I think Ukraine, I think it was. And here we've got the loading capacitor, which is a standard. I think it's 350 cap, 350 microfarad capacitor. Moving on to the this rather unusual arrangement here. So we've got a coil here, some copper coil is about 5mm diameter, and another coil here, which I'll just zoom in on. Now this is actually all part of the plate choke. The main body of the main plate choke is down here, which is about 250 microhenries on a Dacron rod, Delrin rod, sorry. And essentially this is a modification that I've borrowed from a Russian amateur who did quite a lot of work with the GU81s, Echo X-Ray 8 Alpha, Sergei Pasco, and his original circuit diagram used what they call a parallel, I should say he named as a parallel pi circuit, and I've kind of varied this. What I found that on the higher frequencies this choke alone didn't really work terribly well, and I had to essentially switch in this smaller coil for 24 and 28 megs, and this one here, which is about inductance, this is about 9 microhenries. But if you want more details, it's all on the internet. If you Google his call sign, Echo X-Ray 8 Alpha EX8A. So it's quite interesting. And then here we've got, this is actually a decoupling capacitor which decouples the rest of the plate choke, and that's a 4700 puff 4.7 nanofarad at 12 kV, so a big heavy duty decoupling capacitor. And that's more or less it. We've got over on this side, rotating around, we've got our meters. I've wrapped these up in copper foil to just try and screen them a bit because they're right next to the tank coil. We've got obviously we have sort of the usual practice of putting diodes across the meter in opposite directions, and also decoupling capacitor there. Again, that's a 3 kV ceramic. I think it's about 0.01 microfarad thereabouts. Value's not too critical on those. Right, so I think that's more or less the RF deck. So it's fairly standard. There's no sort of, apart from the plate choke, it's all pretty standard pi filter really. Okay, so what we'll do is I'm going to turn the amplifier over and we'll have a look what's underneath. Right, I've taken the back off it and we'll go and have a quick look at what's inside. As you can see, there are a lot of electronics inside here, and the easiest thing is just to go through it, starting at the back. So that's our main RF connector, which is RF in, and then what we have here is, this board here is the input pi filter. Again, this is fairly standard. We're basically grid driving these tubes, and they're arranged in parallel. So the grid impedance of these tubes, because they're connected in parallel, is about 1K. And one thing about grid-driven tetras, which this is effectively, is that the impedance tends to be quite high, and also non-linear as well. And one of the things I found out that it was quite a problem tuning these individual pi filters for the various bands because of the impedance. It's alright when you're sort of matching up to say 200 ohms, you can use sort of standard values, but once you start putting the thing into the assembly with various stray inductances of leads and things like that, the SWR quickly goes out, so you really have to use an antenna analyzer to work out the SWR with the thing in situ. I mean, that's what I found anyway. Right, so down here, this is our main changeover relay, which switches in the screen bias, the screen grid voltage, and also the negative bias. Simple cooling fan there. The tube bases are actually underneath here, and one of them is also down here as well. I don't think you're going to really appreciate what's what with the individual components, and I don't think I'm not going to go into too much detail about that. We'll just look at some various sort of big components to have a look at. This resistor up here is part of the screen voltage regulator system. It's probably oversized. I was doing some experiments with it and I actually ended up leaving it in. It's really just to limit the current into the voltage regulator circuit. It's set at about 1K at the moment. It's a big 5K resistor. Obviously this huge toroid is for the heater supply. That's a 50 amp transformer, the 24 volts, because the heater supply, the filaments are arranged in series of the two valves. Small little toroid there, that's basically for to supply 24 volts and 12 volts for the various boards, relays, etc. This is our negative bias supply, simple string of Zener diodes, providing about up to 250 volts, which you can just tap off if you need to change the negative bias voltage. That's the main HT relay, which switches in the HT. This is our little op amp, which basically is connected to our voltage multiplier there for the HT voltage reading. This pot here again is really just for adjustment of the negative bias level. A lot of electronics on this board here. This is a part of the screen voltage regulator circuitry, and also the trip circuitry for the screen current. So it uses essentially there's an optocoupler there rigged up to that bridge rectifier, which senses the current in both directions and will trip a relay if the current is too excessive on the screen grid. This heatsink, two MOSFETs on there in parallel, again part of the voltage regulator for the screen grid. That board there is just a power supply board for the relays, just standard voltage regulators, bridge rectifiers, etc. And then we've got some indicator lights here, which I showed on the front panel. LEDs. That's the band switch which operates the relays. And what else can I show you? That's decoupling capacitor there, which is for the HT again, to decouple the HT high voltage door knob capacitor. And that's more or less the underneath. It looks fairly complicated, but like my previous amplifier videos, which you might have seen, it's all built in modules and lots of interconnecting wires, but it looks a bit of a rat's nest, but it all seems to work. So next stage, what we're going to do is connect it all up and hopefully give you a demonstration of it working. Mounted the linear back up the right way, and what we're going to do is I'm going to give you a quick demonstration. So everything's turned on, all our warning lights look okay, and the linear's just been tuned up. I've got it connected up to my transceiver here, which is a Yaesu FDDX 1200 standard amateur radio transceiver, and this will give out from 5 to 100 watts, and we're on 14 megahertz, and we're going to be driving it. Well, just to give you the demonstration, I'm actually driving it with about 45 watts RF in. I've got a bird watt meter there. Sorry, a bit shaky there. Bird watt meter showing the RF power out, and we're connected into a dummy load, the old-fashioned cantenna full of oil. So what I'm going to demonstrate first is we'll just key the transmitter, and hopefully I can demonstrate these Mercury Arc Rectifiers working. So we've got no RF in at the moment. You can see the Mercury Arc Rectifiers glowing there. If I take the key off, that looks quite interesting. Okay, so let's apply a little bit of RF and see what happens. So I'm actually going to be on RTTY, RTTY, so we get just a pure carrier wave when I key the mic. So just keep an eye on the watt meter. Zoom in a little bit. It's about 700 watts. It's not as much as I thought I would get actually. I thought I'd get a bit more RF because I'm using 2 of these. But reasonably happy with it. I just zoom in on the meters there when I key the mic. You can see, you can hear the transmitters, the transformers humming away there. So the HT drops a little bit. That's the screen current. Sorry, plate current that is, and then screen current below it. We're running just under 200 milliamps of screen current. So there we are. Just turn. That's the amp. Not a bad project. Quite enjoyed building it. A bit disappointed that it doesn't put out more power, but I think that's it seems to be. I think the grid loading on it seems to be a bit non-linear. With relatively little drive, it'll produce quite a bit of power. 5 watts in, it produces 300 watts on this band, but it gradually tapers off. It gradually plateaus, and I'm not entirely sure why that is. I know my Pi networks have got very good SWR on them, so I don't think, and the transceiver's not throttling back or anything like that. So yeah, a bit of a mystery there is why the output's a bit non-linear. But certainly within you know, if you drive it up to about 40 watts, it does produce, you know, useful 700 watts, 800 watts. Not that you would use that type of power here in the UK. We're restricted to much lower powers. But I rebuilt this for a just for the fun of it, and also it's been quite a nice project. And just before we go, just another view of the valves at the back there, glowing away. And these really do produce quite a lot of heat, so something for the winter to keep the shack warm. Anyway, I hope you enjoyed the video, and hope to see you again.